In this video, we're going to take a look at how measurements are not always as on target as they should be. And so the first concept we need to look at is called accuracy and precision. In our everyday language, we toss around accuracy and precision interchangeably. There's no difference. However, in science, there is a difference. So in science, accuracy refers to a measure of how close a measurement is to the target or accepted value. I think of this as hitting the bullseye. Precision refers to a measure of how close a series of measurements are to one another. So this we think of as a close group. So in terms of this dartboard here, we had 3 darts, 1, 2, and 3. Obviously the red is indicating the bullseye. And so this first target is neither accurate or precise. It's not accurate because there's nothing in the bullseye, and it's not precise because the 3 darts are very spread out. If you look at target B, notice none of them hit the bullseye, so that means it's not accurate. However, look at, they're very grouped close together, so they were precise. Here we have in target C, it looks like pretty close to the bullseye, so they're pretty accurate, and they're also pretty precise because there's a little grouping there. However, D is a better representation of both accurate and precise because they're all in the red and they're much closer together. And so next we look at percent error. Percent error looks at the accepted value. So there's some numbers out there that are just accepted as the correct answer or the correct number, and that's the accepted value. Your experimental value is the value you get while you're measured during an experiment. And then the error is the difference between the experimental and the accepted values. So how far off were you basically? And so scientists prefer to work in percent. It's a little more of a universal language. So then we get this percent error. And the percent error takes the absolute value of the experimental error minus the accepted value divided by the accepted value multiplied by 100. So we can look at that here in this example. The density of aluminum is 2.7 grams over centimeters cubed. This is your accepted value. And a student calculated the value of aluminum's density to be 2.45, and that would be your experimental because the student did that. There was some calculation. So now we need to calculate the percent error. So it says the experimental value, or the absolute value of the experimental minus the accepted value, divided by the accepted, and then you're going to multiply it by 100 to turn it into a percent. So our experimental value was 2.45 minus the accepted value of 2.7 divided by 2.7, your accepted value. And when you do that, you will get 0.093. Multiply that by 100 to get it in terms of percent, and you'll get 9.3%. So the smaller the percent error, the better your measurements were.
Just a reminder, they're serving breakfast.
One strange thing that chemists like is something called significant figures, or sig figs. So there's always some uncertainty or error in any kind of measurement. And this uncertainty is due to either the skill of the measurer or the quality of the tool being used. So if we look at these two rulers, this lower one has a lesser quality because it is lacking the more precise tick marks in the middle. And so the top ruler has a higher quality. We get a more precise measurement. And so if we look up at the top ruler, we know that this is 2.12345, and we could estimate the next digit as maybe a 5. Whereas down here we can know for sure that it's 2 point, but we don't know that next digit. That next digit is that estimated one, and maybe we call that 2.6 on this ruler. And so because we have to estimate much sooner, it is a lower quality of a tool. So significant figures are all of the digits, the certain digits in a measurement, plus one uncertain or estimated digit. So back here, we had the 2 and the 5. Those were certain. We couldn't argue with them. We knew the 2, and then we knew this 5. But this second 5 is our estimated digit. So in this case, there would be 3 significant figures. Down here, this 2 was the for sure digit, and this 6 was the estimated digit, giving us a quantity of 2 sig figs. And so there's some rules, and we can read through them. All non-zero digits are significant, so 1, 2, 3, 4, 5, 6, 7, 8, and 9, so that means 1 through 9 are significant. If the 0 appears between non-zero digits, those zeros are significant. Any zeros out in front of a number are not significant. We call those left end zeros because they're out to the left of the number. Right end zeros at the right end side, are also not significant unless there is a decimal point following it. So 140 with a decimal point would give you 3 sig figs. 140 without the decimal point would only give you 2 sig figs. And then right end zeros, if there's a decimal point, they're all significant. And that is whether we have it in this case like the 620.0, both of those zeros are significant, or if there's just that decimal like we've talked about. So here we can count how many significant figures there are. And remember, sig figs only deal with units of measure. So if it's not measuring, if it's counting objects, there will be 0 sig figs. So pretty much you look for your first non-zero number, so in this case it's the 1, and everything to the right of it is going to be significant as long as there's no zeros. So in this case there's 1, 2, 3 sig figs. In our next example, liters is a unit of measure, so we can look at this one. Go to your first non-zero number, which is the 5, and everything to the right of it will be significant, assuming no zeros. So the 5 and the 1 are significant. That gives you 2 sig figs. Then 204.80 grams. Grams is a unit of measure, so look for your first non-zero number and go to the right. And so then we notice that there's a 0 here and a 0 here. This first 0 is in between 2 non-zero numbers, so we get to count it. It's good to go. This last 0 came after a decimal point, so it's also a valid significant figure. So here we count 1, 2, 3, 4, 5 sig figs. Our next example, 1.90 times 10 to the 5th seconds. So this next one might look a little tricky, but first verify that it is a unit of measure and seconds is. And so since it's in scientific notation, the desire here might be to just look at these numbers out front. However, you do need to expand it. So 1.90 times 10 to the 5th would become 190, 1, 2, 3 zeros. And then your decimal point would be right there. And so go to your first non-zero number, which is the 1, and then go to your right. And so then, since there's that decimal point, all of these zeros are counted as significant figures. And so we would have 1, 2, 3, 4, 5, 6 significant figures in this case. Our next example is 14 beakers. Beakers is not a unit of measure, it is a counting. So we have 0 significant figures. And then our last one, check your units, kilograms. Kilogram is a unit of measure. And so start at the right, find your first non-zero number, go to the right. However, you'll notice that there are some zeros in there and there's no decimal point. So the only significant figure is that 7. So there is only one significant figure. When we do math with significant figures, there's different rules for how we need to round our answers. So when we add or subtract, the answer should be rounded to the same number of decimal places as the measurement with the lowest number of decimal places. And then when we multiply or divide is when we look at sig figs. So your answer has to have the same number of significant figures as the lowest number with the lowest number of significant figures. So we'll practice here. All of these units are units of measure, so we can go ahead and just do this. So when you multiply out the first one, you're going to get this number in your calculator, 1.58256. And so then to figure out where you round it, we're multiplying. So we need to figure out how many sig figs are in each of these numbers. So 0.048 has 2 sig figs, and 32.97, all 4 of those are significant. So your answer can only have 2 significant figures. So 1.58256 would round to 1.6, and your unit would be meters squared. Next example, we're subtracting. So here, when we do the subtraction, we get 2.483. And your answer here, since it's subtraction, can only have as many decimal places as the fewest. So this one only has 1, and here we have 3. So your answer can only have 1 spot after the decimal. And so the 2.483 will round to 2.5, and our unit is grams. Looking at our next problem, when you do the division, you get 2507.745267 in the calculator. Since it's a division, we worry about sig figs. And so here, we only have 4 sig figs. That 0 is not significant because there's no decimal. In 5.81, all 3 of those are significant. And so your answer can only have 3 sig figs. And so in order to do that, you would need to round this up to a 1, 2510 without the decimal point will give you your correct answer. Last example is an addition. So when you add them together, you get 161.2. And so since it's addition, you look at decimal places. And so here you have 1 place after the decimal. And in 90, there's 0 places after the decimal. So your answer can have 0 places after the decimal. So the correct answer here would be 161 centimeters. So again, nothing super complicated, just new rules. So make sure you're checking on the rules as you're going through your assignment.